I'm ready now.
So I hope it is my slide is visible in PPT mode. Evaporators topic. Yes.
Yes, ma'am, it
Yes,
is.
ma'am, it's visual.
Okay. Okay. Thank you. So good morning to you all. Today we will discuss the evaporators and what these are and what the purpose of using it, and then how to proceed for design of this, different components involved in it and all. But before that, let me revise the last class. In the last class we have completed design of reboilers, and we have seen the that example of thermosiphon reboiler, and then force circulation reboiler. Few points we about that we have discussed, and then how to select the reboiler depending upon the condition that we have discussed in the last class. And on that day, probably on Sunday, I guess, I have emailed the that the problem which I have given to you, problem 1 and 2, that you need to submit as an assignment to Ziaul sir, and I will also give a few problems related to that condenser, reboiler, etc. So that I will send. So I hope you all must have received the email regarding that. So please do accordingly. Okay. So that is about the last class, and today we will start the evaporators. Being in final year of chemical engineering, you all must aware of this evaporator, what it is, and how that where it will be used in chemical process, and of course you probably not aware of the design part that we will consider over here, but basic functioning, basic its application and all that you all aware of that, I believe. So let's start with the evaporators. When we consider the evaporator, process is evaporation, which is nothing but the removal of solvent by vaporization of solution that are not volatile. Okay, so that is the main thing, that solvent should not be volatile in nature. And when we remove that by vaporization, we consider that process as evaporation. Okay, it happens at any possible temperature. Okay, and like when we have a glass of water at room temperature, then after some time that water level goes down, so that is due to the evaporation. So it happens at any possible temperature. Okay, so that is the thing, that to remove the non-volatile solvent from the solution. Okay, so it is normally used to produce the concentrated liquid, which is a primary unit before what we can say prime, like a priori unit before crystallization. Okay, so when we consider the evaporation, as we usually remove non-volatile solvent from it, and in most of the cases that is water. So water could be your what we can say, the product. Okay, because that what you obtain by vaporization, the vapors, and then you condense that, so that water or that solution, sorry, not solution, that solvent is at pretty what we can say, it is of good quality, right? So that you can use for some purpose. Another thing is that this concentrated slurry we obtain, that could be our product to further prepare any useful product. Okay, so it is in both way, it could be seen like clear water, uh, or we can say clear solvent, and uh, like concentrated slurry, in both way. Okay, usually when we consider evaporator, it is used in number of plants, number of chemical plants, like pulp and paper plant and sugar plant and like desalination. Okay, and all that we consider the evaporation. And uh, if I say that it is used prior to crystallization, the crystallization, you understand, right? It is basically we work on the supersaturation condition, and this is used to further prepare the crystals out of slurry. Okay, crystals out of slurry, and that formation of crystals required slurry of thick concentration, and that thicker concentration uh, we get from the evaporator. Okay, so usually in chemical process, evaporator is used before crystallization. Okay, so that you understand. And as we have discussed, the valuable product over here could be your that thick slurry, or we can say the clear water, because in evaporation in most of the cases solvent is water only. So either we have clear water, as you can get the example of desalination, where we use sea water to produce the useful water from that. So that is done with that process is called for desalination. We usually reduce salinity of the water and to get the clear water. Okay, so in that case, when we consider the desalination, in that case whatever uh, vapor we obtain from vaporization or evaporation, it gets condensed and we get clear water that could be of useful purpose. However, the slurry we obtain, okay, this thick slurry we obtain, that could be used for making further salt, or in any process where concentrated NaCl is required. So in that way you can get that valuable product as clear water in desalination. When we consider, apart from desalination, when we consider any organic solution which has many components, and we need further concentration of that to bring it to the thicker condition, we can have thick liquor as a valuable product. So in both way you can consider. Okay, it's not like whatever if thick liquor is your priority, you will throw that water which is generated out of vaporization. That water probably may not be of that quality, but that could be used in agriculture and many other purposes, right? So in both are useful for us. Okay, so in that way you can consider the products which are what we can say, which we have out of evaporation. And once we have that we understood the evaporation and the products, we will see the performance of the evaporator, how the performance of evaporator will be judged. Okay, so in that we have two basic parameter. One is the capacity. Okay, so capacity of evaporator, when we consider that how much kg of water could be evaporated in a unit hour. Okay, or we can say in 1 hour how much water we can evaporate. Okay, that amount in kgs. Okay, so that defines the evaporator definition, evaporator capacity, sorry. Okay, the amount of water evaporated per unit hour. Okay, per unit time we can say, but in most but at when we are speaking about industry, the time should be in hours only. Okay, so capacity would be kg of water evaporated per hour. Okay, so in that way we can define. So as more capacity we are dealing with, we can have like uh, we will be able to generate more thicker slurry. Okay, so capacity, what we can say, capacity defines both the things. Okay, and when we consider the how much water is evaporated, that depends on how much heat we are supplying. So it will depend on this q. Okay, and that q will be transferred to the liquid, sorry, transferred to the water using this expression ua delta t mean. Okay, so this is as we are discussing this equipment as heat transfer equipment. So we have the basic equation like Q is equal to UA delta T and then M lambda, M Cp dt and all. So all these equation will remain, will be used here as well. Okay, so in that way you can define the capacity. However, another parameter we have is the evaporator economy. Okay, so economy of an evaporator usually defined as how much water is evaporated per unit consumption of steam. Okay, per unit consumption of steam. Let's say if it is in kg, so how much kgs of water is evaporated per kg of steam consumed, or steam what we can say, inlet. Okay, or steam fed, that is right word. So economy, we consider that how much water is evaporated per unit of steam capacity, how much water is evaporated per unit hours. So in that way, that we define these two parameters. And when we consider this economy is for single evaporator. If I ask you what is the economy of the single evaporator, so that could be like we have considered that as zero point 0.8. Okay, the standard economy, the standard economy of an evaporator, that is usually zero point 0.8. Okay, zero point 0.8 kg of water is evaporated using 1 kg of steam. Okay, because 1 kg of steam you fed, and obviously some losses will be there, so only zero point 0.8 gram, zero point 0.8 kgs of water can be evaporated by that. Okay, and that could be lesser also, but in most of the cases zero point 0.8 is like the that what we can say, the maximum economy. Okay, when we are not using any mean to increase the economy, I am talking about the evaporation process only. Okay, so for one evaporator when we consider, so economy is usually zero point 0.8. However, when we keep on increasing the evaporator number, okay, you must have heard about multiple effect evaporator. Okay, multiple effect evaporator, like we have the we usually fed steam in first evaporator, through which the what we can say, vapor is generated in first effect, and that vapor is used as a heating media in second effect, right? So in that way we can consider the evaporation, and which is defined as the uh, like which is considered as multiple effect evaporator. Okay, so let's say if I'm having three different effects of evaporator, so economy would be like zero point 0.8 into 3. Okay, so 0.8 into number of effects would be the economy, which we consider as the reasonable, or what we can say, good economy. If I'm not, if I'm using some media, some way to increase the that water evaporation by unit consumption of feed, unit consumption of steam, that measures we different measures we are having, and then we can increase the economy. Okay, so what these measures are, how we can increase the economy? Okay, by using multiple effect evaporation. So that is like to because if I'm using three different sets of evaporator and three evaporator in one set, I hope you are getting my point. Three different set of evaporator in which one effect is there. Okay, and if I combine all these, we have the three effects in one set. Okay, so that would be steam will be used in first effect, vapor generated in first effect will be used as a heating media in second, and vapor generated in second effect is used as a heating media in third effect, and so on. Okay, so when we are considering this, we can increase the economy, because in that case it would be simply the multiplication of zero point 0.8. However, when we would like to increase the economy from beyond zero point 0.8. Okay, how we can do that? Okay, that we can do by different way. The first is the vapor recompression. Okay, Vapor recompression, when we are talking about, it means that we would like to increase the temperature and pressure of the vapor which is generated in what we can say subsequent or after effects. Okay, let's say, to give an example, if I'm having let's say 3 effect or let's say 4 effect evaporator system, in which 4 if evaporators are arranged in a series or are placed in a series, and you understand that when we talk about the steam feeding in the evaporator, it is always done in first effect. Okay, so first effect, we let the steam enter, vapor generated in first effect, it is used in second effect, vapor generated in second effect is used in third effect, and so on. Let's say if you would like to reuse the vapor which is generated in third effect. Okay, so one way is that it is already utilized in the fourth effect, right, as a heating media, but you would like to reuse that vapor to, let's say, second effect, or you can say first effect or so. Okay, in that way because as vapor will keep on giving its heat to the evaporator, to the liquid in evaporator, its temperature will keep on reducing, and that you cannot use and at like earlier effects which are already available at high temperature. So you need to compress the vapor to bring it to the high temperature, and then you can use that in maybe first effect or second effect, whatever temperature you would like, you have reached while recompression. Okay, not only temperature, pressure as well. Okay, so in that way we can increase the economy. That is one way. Another way is to flash the condensate. Let's say your steam enters in first effect and exits as a condensate. Okay, what you will do with this condensate? Okay, one way is to recycle it back to the reboiler, to the boiler, to generate steam, because steam is quite pure condition, so that whatever condensate will be there, that is also at pure condition. Okay, so that may be recycled back. Next, if I'm having vapor in first effect and that will be used as a heating media in second effect, the condensate will also exit from second effect from that vapor, right? So that vapor must have certain amount of impurities that may be obtained by entrainment in first effect. Okay, because through vapor some particle may come, so that would not be as pure as the condensate of pure steam. So that would be used, the condensate of the vapor could be used as a what we can say, as a flash. Okay, to generate further vapors. Okay, flashing, you understand, right, that when we have any steam at high pressure, and when it come across suddenly at low pressure, certain amount of that liquid stream is converted into vapor to take heat from the liquid only. Okay, so flashing is to generate vapor and liquid at low pressure in comparison to the inlet. Okay, so because the condensate of vapor, okay, the condensate of vapor will not be utilized anywhere, so we will produce low temperature vapor from it, or low temperature liquid from it, by flashing, and that low temperature vapor, that is used as a heating media in downwards effects. Okay, or downstream effects. So in that way we can consider the because we are reutilizing the vapor. Okay, it does not make any effect in steam consumption, more steam consumption or so, no, but more vapor will be available for for more vaporization, consuming same steam amount. I hope you are getting. So in this way you can consider increment in economy by these a few methods which we have discussed, like recompression, condensate, flashing, etc. Similarly, we have vapor bleeding also. That is another approach, another way. Okay, so in this way you can consider the performance of the evaporator by measuring the capacity and by measuring the economy. Both should be higher. Okay, so that is a few parameters to see the performance. Now next is the operation of an evaporator. Okay, so just in 1 minute I'll start, please. So okay, so next we have the operation of evaporator. Okay, so how this operation of evaporator will be done. Okay, if you consider this evaporator, here I am having this heat exchanger. Okay, this vapor liquid separator and this circulating tube or recirculation pipe. Okay, so the point is when we consider evaporator or multiple effect evaporator, what is the meaning of effect? Okay, what is the meaning of effect? The meaning of effect is the meaning of effect is basically the combination of three different units. Please understand, the meaning of effect is the combination of three different units. One is the heat exchanger, as you can see over here. Second is the vapor liquid separator, and thirdly this recirculation pipe. Okay, so these three components make any effect. Or even if I say the evaporator is there, evaporator is not a single component. It must have all these three components: heat exchanger, vapor liquid separator, and circulation pipe. Okay, in a few type of evaporator, circulation tube may not be there, but in most of the cases these three components are involved, right? So in this way we can consider the effect and the how the complete procedure or operation is conducted. Okay, if you see this because it is what we can say circulated, and in this case, in evaporation, when we consider evaporation is usually occurring in this heat exchanger. Okay, heating media is mostly, in most of the cases, is steam. It enters from here, exits from here, and that is in the shell side, not in tube side. This is a shell and tube heat exchanger. Okay, so feed always enters into the tube. Okay, feed enters from here and then it moves upward through these tubes. While moving upward, it exchanges heat with the, what we can say, with the steam, and then the vapor formation occurs. Okay, vapor formation occurs, and because in this case feed is moving from the bottom and vapor is keep on uh, generating during the movement in the tubes, and at the exit of the tube here I am having one chamber in which vapor and liquid mixture is stored. Okay, that is nothing but simply a cover just for just of higher volume in comparison to this. Okay, So in that case, in that way we can consider the vapor and liquid, and then that vapor and liquid mixture, it enters into this separating chamber, okay, or we can say the evaporating chamber. Okay, this is actually the separation. Vapor formation occurs over here. Okay, so the point is, when the vapor and liquid mixture available over here, it come across with a larger volume. Okay, so as it enters into this larger volume, okay, some uh, what we can say, when we consider this separating vessel, it is nothing but the cylindrical vessel only. Okay, and if you consider this particular connection between heat exchanger and then separator, this connection is tangential in nature, not perpendicular. Okay, it exits from here and enters tangentially to this separator, and the purpose of that is, when it is entering tangentially, the liquid, which is heavier than the vapor, it circulates along the inner periphery. Okay, it circulates along the inner periphery. So the because of that density difference, the vapor settles down, and that or two happens more easily when it is circulating at inner periphery. Okay, so water which is available at the periphery, it goes down. However, the vapor which is generated, it gets separated from the water, and then, or from the liquid, and then moves upward. Okay, and from here we can have the secondary steam. So just a moment, please. Okay, so I'm sorry for the interruption. So when we here we were discussing about the vapor liquid separation. So that happens when the feed enters into this tangentially. Okay, and then the liquid settles down, vapor moves upward, and this vapor is used as a heating media in second effect. So where it will enter next to this. Okay, so this secondary steam will enter to heat exchanger of second effect. Okay, which will be placed over here. Okay, heat exchanger of second effect. In that, inside the shell, this secondary stream will be secondary stream will enter. Okay, so in that way, when we are considering the second effect will also consider all these three component. And further, when I'm having the when we will reach the desired concentration of the liquid, we can have liquid product from here, from this nozzle. Otherwise, that liquid will again enter from here, and then further it will be it gets concentrated by removing water from it by vaporization. Okay, so in that way we can consider the operation where your heat exchanger, vapor liquid separator, and circulating pipe, all these three will be considered as single effect. Okay, and yes, so in that way you understand the operation of the evaporators. Okay, so we will see a few types of the evaporator which are commonly used, and then we will proceed for the design part. Okay, so the types of evaporator, the very important one is falling film type evaporator. Okay, so in as the name says, falling film. Okay, and that film is basically made by the feed, liquid feed. Okay, so liquid feed, like it enters the tubes, and then it moves downward by gravity. Okay, so because of that it is called as falling film. Okay, falling film type evaporator. So liquid is fed to the top of the tubes and flows down the walls as a thin film, therefore it is called falling film. Okay, vapor liquid separation in this case is usually placed at the bottom, because liquid is entering from the top, and then that through vaporization is vapor is generated, and that vapor liquid mixture moves down, because there is no place to move upward, because continuous liquid is coming from the top. Okay, so that vapor and liquid mixture and moves down, and then it enters into the vapor liquid separator. So this is the only type of evaporator in which vapor liquid separator is placed at the bottom. Otherwise, in all other cases it is at the top. Okay, so this is used for concentrating heat sensitive material. Actually, falling film evaporator, when we are considering, because it is having separating vessel or separator at the bottom, so in that case recirculation is not considered. Okay, and therefore it is mostly used in heat sensitive material, where heat sensitive material are involved, such as food and beverages and all. Okay, like concentrated juice, if you need to make that, you need to further concentrate in the evaporator. Okay, and that in that case you cannot again and again circulate or feed the juice to the heat exchanger, because that is at quite high temperature. So liquid should, the feed should not be re-enter into this. Okay, that is only one only once it will enter. Okay, so therefore it is used for heat sensitive material. Here like one video is there that you can see. So this is the feed inlet, liquid is entering from the top. Okay, so in this way, uh, liquid is fed inside the tubes. Okay, so it has multiple tubes, and inside the tube, liquid is filled, and you see that it fills as if it is making a thin film around the inner periphery of the tubes. There, and because it is moving down, that's why it is called falling film. In this way, feed enters in this. In this way, vapor formation occurs, which will move down with the liquid stream. And in this way, vapor and liquid is collected over here, and that some concentrated liquid you can obtain here. However, the vapor with along with some entrained liquid, it moves in this through these pipes. So if you see, this is, if you consider this pipe, this is not the perpendicular pipe, this is a what we can say tangential pipe, okay, which creates automatic circulation in this vapor liquid separator that you can see. So vapor moves up and liquid moves down automatically. So in this way, you can see that feed enters from the top. Okay, vapor liquid separator is attached or is connected at the bottom, and then there is no circulation pipe. Okay, otherwise this should be connected with this head. Okay, so this that connection is not given, so circulation is not possible over here. Okay, and that too, it is because of that it is used in heat sensitive material to concentrate. Okay, so in that way you can have this falling film evaporator. Next we have the forced circulation type evaporator. uh, if you consider this, the liquid is sent by the pumping to cause forced circulation of the liquid inside the tube, and this is very useful for viscous liquid. Okay, so usually feed enters from here, sorry, feed enters from here, and that you can see as because of pump it is entering, otherwise that can be entered automatically. Okay, so this is the heat exchanger, then we have vapor liquid separator, and then here we have the recirculation pipe. So because that vapor liquid separating that whatever vapor is generated, it enters into the condenser to have the that clear liquid as the product. Okay, so because of this pumping, the that circulation is maintained, and therefore we call that as forced circulation, and that happens when we are dealing with more viscous fluids. Okay, or fluids having high fouling tendency to increase the uh, flow, to increase the velocity. Okay, so in that way you can consider different types of evaporator, and here we will start the design of multiple effect evaporator. So if you recall the first class of where we have discussed the introduction of this course, there we have discussed that when we are considering evaporation design, what is the meaning of design? The meaning of design is to find out heat transfer area of the heat exchanger. Secondly, to find out the steam consumption. Okay, so the design of evaporator means the computation of heat transfer area and steam consumption required for a specified separation as a specified set of steady state operating condition, at a specified set of steady state operating conditions. So for a given condition, how much separation is achieved, and to achieve that separation, we how much area we need to provide, and how much steam consumption should be there. So that all we need to consider. Okay. So in that way, we have to carry out the design of multiple effective evaporators. So first of all, let me discuss the functioning of multiple effective evaporator. We will start with triple effective evaporator. Okay, so these are the three different effects, and each effect, when I'm telling, each effect includes heat exchanger, separator and recirculating pipe. Okay, that you should keep in mind, this box and this box individually. Okay, so in this case, feed enters from the uh, what we can say, feed enters from the first effect, and it exits from here. The concentrated liquor exits from here at L1 flow and T1 temperature. T1 is the temperature of this effect, and here I'm having F flow of the feed, TF temperature of the feed, and XF concentration of the feed. Okay, so in this way we can have that concentrated product from first effect is L1 and T1, and this L1 we are considering, this is when we have the what we can say, the uh, quite thick slurry. Okay, it's not like only one way we can consider. So in that way you can have multiple what we can say, circulation through the recirculation pipe. So after that, whatever product we are taking, that is L1, not the liquid which is exiting the vapor liquid separator. Okay, which is exiting the system, that we are considering over here. I hope you are getting my point. So L1 is the liquid flow that enters into the second effect and further gets condensed, further gets concentrated, and exits the second effect as L2 at T2. It will enter into third effect, and then finally I am having L3 T3. Okay, so if you consider this type of flow, okay, this type of flow is usually forward flow. Okay, you must have heard about different flows. You must have heard about different flows, different flow patterns, I should say, different flow patterns in multiple effect evaporator. That could be your forward feed, backward feed, mixed feed, okay, and parallel feed. So forward feed that you are seeing just now, backward feed, that feed enters from the bottom and then moves, exit third effect, then enters second effect, exit second effect, then enters first effect, and then from finally the final product exits from first effect. Okay, so in that way you can have backward flow. Mixed flow would be like uh, it enters into second effect, then move to first effect, then move to third effect, right? Like 2 1 3 or 2 3 1, yeah, in that way, like 1 3 2, any combination apart from this forward and backward, that is called as mixed flow. Okay, what is parallel flow? Parallel flow is that this feed is divided into number of effects, and each part of the feed enters to single effect and exits from single effect, and then the product will be combined. Okay, so parallel feed is feed divided into number of effects. Each part enters into that single effect, and then product, after getting concentrated product, exit from each effect, and then they can mix together. Okay, so that we can consider as the uh, flow. So that flow pattern, when we are talking about, it is only based on feed movement. Okay, it does not consider any vapor movement. Fine. So please keep in mind that sequences depend on the flow of the feed, or flow of the feed or liquid in the system, not because of the vapor. However, when we consider the vapor movement, vapor enters the third effect at VO flow rate and at TO temperature. Okay, then it what we can say, supplies heat. Okay, and then we can have the, and then we can have the vapor which is generated into this, and then that vapor enters as a heating media in second effect. Okay, so if you are considering this v1 is the vapor which is exiting the first effect, and that would be F minus L1. F is the total feed, L1 would be the product from this first effect. Okay, because whatever v1 is generated, that v1 will generate only from the feed. Okay, and whatever remaining part is there, it will exit as a liquid. So you can make the mass balance over here, v1 should be equal to F minus L1, to reduce the reduce the parameters. Okay, because L1 you are considering over here and here as well. So if you consider V1, F is usually known, so only L1 would be the parameter. Otherwise F, V1, L1, all these would be different parameters. Okay, so now vapor is generated in first effect, enters in third effect, and in third effect again the vapor is generated as V2, which is nothing but L1 minus L2, just the mass balance you can see. Okay, and then if V3 exits, similarly V3 exits from the last effect. Okay, and where it will go further? Okay, it will go to the condenser, and this whole system. Okay, whole system like evaporator, condenser, all these will be connected with the vacuum pump at the end, at this end, right? Vacuum pump will be available at this end, at the last of the system. Okay, and last of the system means all effects plus condenser. After that we have the vacuum pump. Okay, now the when vacuum pump is there, the purpose of the purpose of vacuum pump is to generate the vacuum. Okay, it's funny. So when we say that it creates vacuum, okay, if it is available over here at the end, okay, maximum vacuum it will create in this effect, right? And just more than that, sorry, just less than that vacuum will be created over here, and just less than that vacuum will be created over here. The point is, as we move away from the vacuum pump, okay, vacuum will keep on decreasing. I hope you understand. And as I have told you that vacuum will keep on reducing, keep on decreasing, it means the pressure will keep on increasing from vacuum pump to the that steam end. Okay, I should not say feed end because feed may differ, but steam will always enter into first effect and then move sequentially towards the uh, last effect. Okay, and if you need to bring this V2 at V1 temperature or so, you need to compress this. Okay, we have discussed vapor compression, na? So that will be used for this purpose. Okay, so the point is we have the vacuum, and that vacuum will create vacuum in which part? Okay, it will create vacuum in vapor liquid separator, recirculation pipe, and tubes of heat exchanger, not the shell. Okay, because tube feed is entering into the tube, and then that tube are again connected with the vacuum. Okay, so because of that low pressure or vacuum is there, the liquid or feed automatically enters into the tube and moves upward because of the vacuum condition, because feed is entering at high pressure. Okay, so in that way, what we used to consider over here, few points like according to the feed flow, different pattern of flow can be decided. That is one point. Second point, steam will always enter into first effect and then move forward. Okay, steam flow will always be forward. Okay, that is point number 2. Point number 3 is the vacuum pump is attached to the end of the system and it creates vacuum in the effects in decreasing order. Okay, so it what does it mean? That it could have maximum pressure, then the pressure of P2, sorry, P1 would be higher than P2, would be higher than P3. So in that case, because you can read the vacuum pump unit, sorry, vacuum pump value, you can read, right? So it means that vacuum pump would be corresponding to vacuum of last effect, either it is third, fourth, nth, whatever. Okay, but last effect pressure is usually a known quantity because vacuum pump is there, and from that we can read the vacuum unit. Okay, vacuum value. Okay, however, when we are considering these two effects, after steady state some pressure is usually maintained over here, but of course P1 would be higher than P2, P2 would be higher than P3. Okay, so P3 in that case will always be a specified parameter. Okay, I hope you are getting all these points. Specified parameter, okay, not the variable. However, P1 and P2 could be variable. Okay, that will be adjusted depending upon the calculations. So that we will see. Now the point is, because vapor is evaporated, water is evaporated, and that usually evaporate at saturation condition. Okay, so whatever pressure P3 you have fixed, corresponding to that T3 you can also fix considering steam table, right? Just 1 minute. Okay. So in this way you can understand the multiple effect evaporator and the functioning of that. Okay. So I hope you are getting that T3 or P3 is the known quantity or the specified parameter. V naught, T naught is also what we can say known parameter along with this feed condition. Okay. All these are known parameters. Okay. Now, when that steam enters, the condensate exits. Okay, this vapor enters, condensate exits. Vapor enters, condensate exits. So, in that way, you can have the condensate exit also, which we have not shown in the earlier diagram, so that you can see. Okay. Now, to start the design of multiple effect evaporator, we will first derive the governing equations related to that, related to the evaporators. Okay, so let's see that. For first effect, if I am telling, to derive the governing equation, we need mass and energy balance. Okay, and that mass and energy balance, wherever I am drawing, okay, wherever I am drawing, I usually put an envelope around it. Okay, so if you consider this first effect, so this is the envelope. Okay, so this is the envelope, and when we consider mass and energy balance, we will consider only the streams which are exiting and entering to this envelope. Okay, so let's make the energy balance. We have the inlet like this feed. Okay, we have inlet like this steam, and we have three exits V1, okay, L1, and this condensate, right? F into HF is the enthalpy of feed, okay, F is the flow rate, F into HF plus Q1 we will see what it is. So these two are plus quantity minus V1 and capital H1, okay. V1 is the vapor which is exiting from first effect, capital H1 is the enthalpy of vapor, okay, which is associated with this V1, okay. Enthalpy of vapor, you understand, that is enthalpy of liquid plus heat of condensation, okay. So that is basically H plus that should be I think enthalpy is there, so that should be lambda plus H naught, okay. Sorry, H1 is small h1, because that is the enthalpy of the liquid, okay. Enthalpy of the liquid plus latent heat is the enthalpy of the vapor, right? So capital V1 capital H1 minus L1, as it is in liquid phase, small h1 would be involved over here as an enthalpy of liquid, okay. So further consider that we have FHF as it is. Now this Q1 we have considered as V naught lambda naught, okay. As I have told you that this is the uh, what we can say stream is steam entering, and this is the condensate exiting, okay. So exiting condensate will involve enthalpy of liquid with it, okay. So that should be V naught small h naught, if we are talking about this, okay. V naught small h naught, okay. In that case this we will consider as V naught capital H naught. Here capital H naught should be there, okay. And in this minus V naught small h naught, that should also be there, another term, okay. So because enthalpy of liquid is enthalpy of vapor is enthalpy of liquid plus latent heat, so only latent heat will be available over here, rest will be cancelled out, okay. You can do that and resolve on your own. Further V1 we have replaced with the it should not be L naught, it should be F minus L1, okay. F minus L1, that should be V1, okay, minus L1 H1, right? So when we consider the when we open up this capital H1 capital H1, so that should be lambda 1 plus a small h1, okay. So we can assemble the h, we can rearrange basically. So this equation you can obtain as enthalpy balance in first effect enthalpy, and this is also because of mass balance, okay. So enthalpy balance is this. Second, we have the rate equation. If you see, all these parameters are enthalpy of the stream only, like mcp dt, okay, m lambda, like that, okay. So that is enthalpy of the stream only. Rate equation is how much heat transfer will occur, okay. So that could be your because heat is taken by this steam, that is V naught, okay, and it is supplying V naught lambda naught to the system. So V naught lambda naught, that is equal to U1A T naught minus T1, okay. So T naught should be this, not Ts, okay. So T naught minus this effects temperature, that is capital T1. So U1A T naught minus T1, and that should be equal to V naught lambda naught. So in that way we can have the first effect equation. I have not considered over here a1, because in this we consider that area is equal, area is same for all effects, okay. So that we will see further. So u1 is the heat transfer coefficient in first effect, and how we will obtain that u1, okay. That vaporization or boiling is occurring inside the tube, okay. Condensation is occurring at the shell side, okay. So in that way you can find, you have read both the both the contents, and reboiler as well as condensation, both you have read. So you can find out u1, okay. U1A, that is area of heat exchanger of that effect, okay, area of heat exchanger of that effect, okay. And that uh, T naught minus T1, that I have already told you, that is equal to how much heat transfer is occurring. So that is V naught lambda naught. Okay. So these two equation, this equation and this equation, these two equation belong to first effect. Okay. And further, if I ask you to derive the equation for second effect, there is no need to derive it. You can simply extend this. Okay. Like if you consider for second effect that F should be L1. Okay. L1, and here I am having H1 minus H2 plus V naught lambda naught. V naught would be your V1 lambda 1. Okay. V1 you can replace with F minus L1. Okay. F minus L1 would be V naught, sorry, V1, and that V1 will appear over here into lambda 1 minus F minus L1. So minus, in that case you can consider L1 minus L2, L1 minus L2, and this should be lambda 2. Okay, similarly here I am having U2A T1 minus T2, and that should be equal to U1 lambda 1. You can U1 uh, lambda 1 and U1 you can open up as F minus L1, right? So in that way you can have the equation for subsequent effects. Like this is for second effect, you can tally what we have discussed, the same thing has come over here. Okay, so in this way we can have equations for second effect and third effect. The point to consider over here is each effect can be represented by two governing equations. Okay, each effect can be represented by two governing equations, right? So this is for effect 1, for effect 2, and for effect 3. And here I am having the specified parameters. Specified parameters could be what? Your that F, all these parameters would be known, or we can say specified parameters. And unknown parameters would be what? See, here you are having only T3, but T1, T2 is, you do not know. So T1, T2 could be the unknown parameters. Only L3 you are aware of. Okay, because you usually know the X3. X3 means the concentration of the product. Okay, that you know well before that the feed is available and this and that at this particular concentration, which is going to be at this particular value at the product. Okay, so X3 is usually known, so you can make the component balance. FXF will be L3X3. In that way you can find out X3 or L3. So L3 is not unknown quantity over here, but yes, L1 and L2 will be unknown. So T1, T2, L1, L2, these four parameters are unknown. Other is the that your area. Okay, so area, because we consider equal area, so that is one quantity only, and apart from this you could have this V naught. Okay, so total 6 parameters you may have, and equations, when you are considering, we have 6 equations only. Okay, 6 equations, 6 and unknown, so unique solution will exist, right? So that you must have read in your schools also. So that should be the unique solution we need to consider. Okay, now once I'm having this unique solution, we can we can do one thing, that we can solve the 6 equations simultaneously and get all 6 parameters. But it is not very easy to solve 6 different equations simultaneously, so we will adopt another procedure for that, for doing that. And that should be like, all these parameters are known: V naught, T1, T2, L1, L2, and A. Okay, 6 parameters, all these are. Okay, just a moment. So the procedure which we are going to follow over here is the Badger-McCabe method, and that this method includes the following steps. Like, we usually assume values of the temperatures and for first and second effect, because six parameters you understand, you aware of. So we will take some of the assumptions to find out to find out some of the values, and then we can reduce the number of variables to find out the correct solution using simultaneous, by solving the equation simultaneously. Okay, but for that we need to reduce the number of variables, so that we can do by assuming temperature for first and second effect. How that assumption will be considered, that we will see. Determine evaporation rates L1, L2, L3. Okay, you please consider all these steps. This I will demonstrate or illustrate with the help of one example. Okay, so use the heat transfer rate equations to find out the surface area A1, A2 and A3, and if areas are unequal, redistribute the temperatures so that you can have equal area into consecutive iterations. Okay, so this is because you have assumed a few parameters, so iteration must be done. Okay, so in that way you can consider the Badger-McCabe method. Okay, just give me 1 minute time, I will restart. I will start again, don't go anywhere, just 1 minute please. Yes. uh, So in this way we can have different steps involved in Badger-McCabe method, and let's discuss this with the help of one example so that approach is clear to you. Okay, so here I'm having one example which is like for triple effect evaporator system, and it is designed to concentrate solute from 10% solution to 50% by weight. Okay, so xf is zero point 0.1 and x you can have forward feed, so x3 should be zero point 0.5. Okay, so that concentration of feed and product, that is already given. Feed rate is given over here, and it enters the first effect at 100 degree Fahrenheit. Forward feed is to be used. Okay, saturated vapor at 250 is available as heating medium, and the third effect is to be operated at absolute pressure, which I have told you that this is connected to the vacuum, and that usually the third effect pressure or temperature is known. So it is 125 T3, and we need to neglect the boiling point elevation, and that you must have read in your heat transfer course. And apart from this, we are given other parameters like specific heat should be 1 BTU per pound degree Fahrenheit for all feed and all other liquid streams. Otherwise, it is it is composition dependent. Okay. And lambdas are equal, okay, for calculation purpose only, nothing else. Otherwise, you can consider different one also. Okay, u1 500, u2 300, and u3 200. In this way, the overall heat transfer coefficients are given. And the first step is to find out the temperature, unknown temperatures. Okay, and unknown temperatures are T1 and T2. T3 is known to us, and T naught, that is steam temperature, that is also known to us. Okay, so to find out this, how to find out this? To find out that T1 and T2, we will assume a few, we will assume that equal heat transfer is occurring in each effect. Okay, what we are assuming, that equal heat transfer is occurring in each effect. Okay, and the total temperature distribution in the system should be T naught minus T3. Okay, please keep in mind it should not include TF. Okay, because TF is the feed side. Okay, but the temperature which is available to transfer the heat, that should be the steam side and effect side. Okay, so in that case, the first temperature would be your steam temperature, and in the system last temperature should be T3. Okay, not feed temperature. Don't consider feed temperature over here. Okay, so it should be T naught minus T3, and all values are given, so that total temperature drop available in the system is 125. Okay, which will be distributed in all three effects. All three effects means delta T1, delta T2, and delta T3. Okay, so in that way, so summation of delta T1 plus delta T2 plus delta T3 would be equal to this 125. Okay, so we need to assume equal heat transfer in each effect. Okay, equal heat transfer means that if Q1 is transferring in first effect and Q2 is transferring in second effect, Q1 should be equal to Q2. Okay, further, Q1, how we can write Q1, like U1A delta T1. Fine, and that should be equal to U2A delta T2 for Q2. Okay, because area we are assuming as same, so that should be delta T1 U1, which is equal to delta T2 U2. Okay, so we can resolve like this, delta T2 by delta T1, and that should be equal to U1 by U2, and that should be 5 by 3. Okay, similarly we can write delta T3 by delta T1. That is quite obvious that because we have assumed equal heat transfer in each effect. So Q1 plus Q2, sorry, Q1 will be equal to Q2 will be equal to Q3, like that. Okay, so in that way you can consider delta T2 by delta T1 and delta T3 by delta T1. Now total driving force I am having is delta T, which is equal to 125, and that should be equal to delta T1 plus delta T2 plus delta T3. Okay, so this term you can divide by delta T1 and multiply by delta T1. Similarly this term. So this term and this term. Okay, this term and this term, that you have already done over here, right? So in that way you can calculate delta T1, which is which you can find as 24.19. Then delta T1 you can find out delta T2 from here, and delta T3 from here. So everywhere you see, this is, it depends on the assumption that equal heat transfer is occurring in each effect. Okay, so I'm having delta T1, so we can find out T1. Okay, delta T1 will be equal to T naught minus T1. Okay, delta T2 will be equal to T1 minus T2. Delta T3 will be equal to T2 minus T3. And T3 will be same. Don't calculate this and then find out T3 would be like 125.4 or 124.67, something like that. Don't do that. Sorry, T3 will always be 125, right? So in that way you can find out T1, T2. T1, T2 you can find from here. Okay, now once you are having delta T1 and T2, we need to find out the flow rates. Okay, L3 is usually known because concentration you know already, so that should be concentration is given for feed and product. So you can make the component balance, so Fxf would be equal to L3x3. So all parameters are known to us, so L3 we can find out by this. Okay, whether you carry out other iterations or not, this value will not change. Okay, because all these values are not assumed value, they are actually given. Okay, so you cannot play with it. Okay, now once I'm having this L3, next step is to find out L1 and L2. Okay, so these are three governing equations for enthalpy balance in all three effects. Okay, this we have already derived. So if you consider this particular equation, here I am having this V naught. Okay, which is unknown. Okay, other parameters like T1 you know already, L1 you do not know, but V naught also you do not know. And if you consider these T2, okay, here I am having L1 unknown, T1, T2 I know, F, L1, L1 unknown and L2 unknown. Okay, similarly here I am having L2 unknown and L1 unknown and L3 that you know already. So if you consider these two equations, only L1 and L2 will be the unknown quantities over here. So we are having two equation and two unknown, and L1 and L2 other parameters are known to us. Okay, so L1 and L2 you can calculate by solving these two equations simultaneously, and which is not a very tough task. You can solve two equations simultaneously. Okay, so once you do this, you will find out L1, L2 and L3 you have already calculated like this, right? So here I am having three unknowns, V naught, L1 and L2. So once you have L2 and L1 over here, yes, L1 and L2 from here, you can find out V naught from the first equation. Okay, so simultaneously solving two equation, we can get L1 and L2, which are coming like this, and thus we can find out V naught using first equation. Okay, so this is the flow rates of first iteration. Secondly, we need to find out the areas we can compute as a1 v naught lambda 1 by u1 delta t1. Okay, and that you can find out, right, because you know all rate equations. So rate equation will give you a1, a2 and a3. Okay, if you see all these three areas are different, we have assumed equal area, right? So we need to consider the average area, and then we will find out that how much average area is deviating from these values, and accordingly we will adjust the temperature difference. Okay, so equal step 4 is to find out the new set of delta t's. Okay, because we have calculated based on equal heat transfer, which we need to relax further. So that you can do that average area weighted to temperature difference. So A delta T1 would be equal to A1 delta T1 plus A2 delta T2 plus A3 delta T3. So this is the average area you can obtain, and you see all these areas are different than this, so we can find out new set of delta t's. So from here onward we have second iteration. Okay, from here onward till here we have first iteration. Okay, so from here delta t1 should be a delta t1 by a. Okay, so you can find out this delta t2 and delta t3, which you can find like this. So once you have all these value, you can further calculate t1 and t2, and then L3 will be fixed, L2 L1 L2 you need to find, and then V0 you need to find, then these areas you need to find. So 6 parameters you should keep on iterating till you will find equal values of all in two consecutive iterations. Okay, as you can see this table. Okay, so along and so in 4 5 iterations we can have all values are equal in two consecutive iterations, almost equal. Okay, here we are getting the difference at third place, that is okay. So in that way you can you can complete the design of evaporators, multiple effect evaporators. Okay, so you can do that. This is about the multiple effect evaporator design. And if you see the heat transfer area we have obtained like this. Okay, and steam consumption is this. So that is only the purpose of design, but that too you cannot obtain until unless you will not obtain rest uh, 4 parameters. Okay, so only all 6 you need to consider together to find out V dot and area. Okay, so in this way a design of multiple effect evaporator you can carry out, and that is all about the evaporator. And that's all from my side for today. Okay, I hope through the example things are clear to you, and we will solve. I will give you the problems also so that you can try on your own. Okay, so in this way the evaporator design is completed, and that's all from my side for today. So thank you everyone for your patience, and if you have any query, please discuss. So I think that is no queries there, so we will stop over here. So thank you everyone for your patience. Thank you.